Hello, and welcome to a demonstration of active camouflage. But this video isn't actually about hiding better, it's about defeating camouflage using advanced technology. Now, you probably already know how camouflage basically works. One of the easiest things to pick out is a silhouette. You can see the edges of my silhouette against the background. So it's pretty easy to pick me out of the background. But if I come down here and I get sort of lower to the ground, now I'm not quite as obviously a silhouette. Now the color of this shirt contrasting against the brown is what the issue is. Now I could try some different colors, but now the lightness and the darkness of these colors, which are correct, those are the things that stand out. But even if I got those right, there's a fourth issue, which is movement. The more that I move, the more that your eye is drawn to me, who I am trying to hide right now. So yeah, those are the four basic elements of camouflage. Those are the four things that we need to try to hide or get rid of if we would like to become invisible. Now, I am not an expert in tactical application of camouflage, but I realize something. I am an expert in animation and visual effects, and compositing elements together in a television show or a movie is almost exactly the same. The thing that your eye notices in a bad composite is going to be bad edges, or it's going to be stuff being the wrong color, or the wrong lightness and darkness, or the motion not lining up. And your eye is really well developed to see this. You have seen bad composites of stuff in movies and TV shows and instantly knew that it was wrong, even if you couldn't quite put your finger on why. And so this idea of camouflaging something that shouldn't be in a real environment, or integrating something that isn't in a television or movie environment, are really the same problems, and you have the exact same hurdles to overcome. I think that's kind of an interesting thing for us to explore right here. And to experiment with some of this stuff, we're going to look at some of this footage inside of After Effects. Now, After Effects is a compositing and animation package. It's really useful for combining different elements together to create the illusion of realism, but it's also a handy image processing tool for trying to find camouflage inside of other images. Bad movies and bad camouflage both work really nicely inside of After Effects. Now, in today's world of artificial intelligence and computerized learning and visualization tools, the obvious question is, can spotting bad camouflage be programmed into a machine? And the answer is yes, but the human brain and the human eye are really well suited to picking out those kinds of abnormalities that bring attention to a camouflaged object. And so let's talk through some of the ways that we might be able to use computerized tools to amplify some of the differences so that we can more easily pick out camouflaged objects, whether they are people or whether they're vehicles or whether they're buildings or something else. Now, the way that people always try to solve this problem is more data. If you give the computer more information, it's going to be better at pulling a camouflaged object or individual out of all of this. Now, there's a bunch of different ways to record and visualize information. This is a color image that you are looking at now, made up of red, blue, and green channels. This is the blue color information all by itself. And it's kind of dark because there's not a lot of blue things in this image. And then this is the green image. My shirt should be brighter because it's reflecting more green light into the camera. And then this is the red channel. My face should be brighter because, you know, it's mostly red. And then this is near infrared light right here. It's very interesting looking. It reveals a few things that the red channel doesn't. So compare the red and the near infrared. And then this right here is heat information. It's not really even behaving like light. There's not shadows on my face anymore. There's just heat and cold areas. And stuff that is invisible to one particular color image is going to be visible on a different one. So for example, this transparent water right here is not visible until you switch to the heat mode. And then you can see that we've got some coldness happening down here. Strange. What does it look like?
It looks like you have stripes on your face. That is so cool. Right here.
Very strange. The way we shot that footage is with multiple cameras. So up here we have our regular Sony camera that we use for most of our stuff, regular lens, and that gets your red, blue, and your green visual spectrum just like the eye sees it. Down here we have our full spectrum Sony camera, which has been used for a whole bunch of T-Rex arms videos specifically about night vision. And this right here means that only infrared light is getting past this filter. And then up here we have our little thermal camera plugged into a phone, and everything is bolted together into this very lightweight and sturdy rig. Simple, easy, straightforward, and the idea is, of course, that if I can't see something hinky in the visual spectrum, I look through my infrared viewfinder, and if I can't see something there, I check thermal. Now, you might assume, because this is YouTube, that thermal just always works. It is the magic bullet. It sees everything and it defeats all camouflages. And that is partly true. As tactical gun tubers have said, if you don't have thermal, you're gonna die.
If you don't have thermal, you're gonna die to somebody who does use thermal.
That is true, but thermal isn't omniscient and it can't actually solve all the problems. There's a bunch of ways in which thermal can be confused, both by natural environmental stuff and people trying to confuse thermal. So I've been using this thermal device to experiment with a whole bunch of different situations, and what I've discovered is kind of interesting. On a day like today, when it is over 98 degrees, and I am 98 degrees, I don't stick out of the environment quite as much as you might think. But I do stick out because I am emitting heat in a way that these tree trunks and these leaves kind of don't. But if you go up on a hilltop where there's a bunch of sun-baked rocks and mud, those are giving off 98 to 100 degrees worth of heat. It is actually surprisingly difficult to pick out, say, small children walking in the woods amongst all of that visual clutter. So, more data is the answer, sort of, depending on the situation. And the problem is gathering all that data requires a little bit of clunky extra stuff. And then viewing and processing all of that data is kind of a chore. So once we have stuff from our super janky rig over here, we're gonna put it into After Effects. Now there are plenty of commercial off-the-shelf thermal fusion units, and they can combine images and thermal in different ways. The simplest and probably most useful is to just detect the edges of the thermal and overlay that on top. That will allow you to see kind of highlighted the hot spots in the image while still seeing all the color information. Another way to do it is to extract the details from the color image and apply those on top of the thermal image. Another way to do it is to highlight just the hottest areas with bright red. This works well when you're using, say, monochrome night vision, green phosphor type night vision, or you're at night when there aren't any bright colors and the bright color tells your brain that you're looking at a hot spot. There's a bunch of different ways to combine these different things so that you can see them all at once. But already, did I mention our camera setup was janky? We're having some parallax issues. I kind of have to manually line up some of these different things based on where we were filming, whether it was close or far away, because of just the distance between the two camera lenses. The parallax issues, we'll talk about those later. If I tweak my values a little bit, you can see that this is actually a pretty good way of highlighting thermal stuff inside of the visual space, making it really easy for my eye to see that there's something that stands out in the thermal spectrum, even though it's not quite as visible in the visible spectrum. So that's why this edge highlighting mode is so popular in the various handheld and head-mounted fusion devices that exist on the market now. Now let's take a look at our infrared camera. So in the infrared spectrum, this particular green mesh netting really stands out. It's not the world's greatest camouflage in RGB, but it is the right color. It is basically the right value to blend into the background somewhat. But on the infrared spectrum, it really kind of pops out. It doesn't so much stand out from the live foliage, but some of the background. And we could try our find edges trick to see if we could make some obvious correlations here. It does help it stand out as a really clear like silhouette, but it adds just so much noise to the image. It's going to require a little more I guess, a cleverer approach to try to figure out how to highlight this particular shape amongst all the leaves in this infrared spectrum here. You know, one sensor that we don't have on this camera is LiDAR. Being able to capture depth information is valuable for picking things out of the background, things that should be closer or further away than they appear. That is a super handy thing. You can kind of tell when you walk around with two eyes, you have great depth perception. When you watch videos that are shot through a nice camera with beautiful bokeh, you can tell that stuff in the background is out of focus. But even though we don't have a LiDAR sensor, I think we can simulate this and use it to draw some more outlines, build some silhouettes that your eye will catch. I'm going to use a experimental AI tool to try to grab some depth information. It's not amazing, it's kind of soft, but it can definitely see, let's turn this on, you can definitely see that there's something behind these leaves, so better than I anticipated. So now that we have our depth data, let's see what we can do with it. Let's try our Find Edges tool again. That's not super useful because I really want to specifically look at a range, a distance range where there's something behind the bush. So let's try to really isolate it. You know, now we can look at different depths of the scene, what is near and far, and it's kind of interesting. It's not really helping us pick out a whole lot of edge detail, even though it can see the edges of this camouflage hiding behind the bush. So it's interesting, but ideally we would have real LiDAR data, so we'd have a little bit more granularity. It wouldn't be simulated, it would be the real thing. But now you're talking about just tons and tons of information. Another important thing to be capturing or looking for is motion. When you're recording video, obviously you're getting motion, but motion is great for detection. You can catch motion out of the peripheral vision of your eye and you're instantly attentive to it. So you're really good at that. And computers are pretty good at sensing and detecting motion, but pretty much only from stationary cameras. If your camera is locked off, like a security camera, that's great. But if your camera is handheld, like this thermal footage from the top of the woods, I'm trying to see these little guys walking between the trees, but it's going to be tricky to do that because the camera is moving around. Now I can detect motion. The white lines are motion, the difference between different frames, and I can't really pick the people out because I can just see the whole thing moving. Now, there's a couple of tricks. We can stabilize this footage. So now, even though the camera footage is moving around, we've stabilized it in place. So we should be able to see these little figures walking between the tree trunks pretty easily with our motion detection. And there are definitely a few frames where they stick out, but there's still just a little bit too much motion in this low-res thermal image. Let's try this regular RGB image. This is a much more stable camera shot and I have stabilized it. And so now you can actually see the individual people walking between the tree trunks. But it's not a completely clean image because there's a lot of wind moving the tree leaves around. It is interesting how the big motion, the people who are moving faster and farther from frame to frame than the other moving leaves and other stuff that's going on in the wind, do stand out as white pixels, and we can highlight them and draw little boxes around them that say this area needs attention. So there are ways that you can overcome moving cameras. You can look for stuff that is moving faster and more than other stuff that is in there. And there's a ton of research on this that has been done in the commercial sphere. If you're interested in that, I would look into ACM, which is a scientific journal. I think it's the Association of Computer Machinery, and they have a conference called SIGGRAPH, and they publish all kinds of white papers on machine vision and analytics. There's plenty of secret stuff being done, sort of Department of Defense and DARPA, but that you don't really find out about until later. ACM and SIGGRAPH and some of the other folks at Stanford who are working on this stuff, they publish their results, and oftentimes the algorithms in the code, and you can tinker with it and you can play with it, and sometimes it makes its way into After Effects. That's how I stabilize the footage, by the way. Stuff that people were working on a few years ago at Stanford, published in ACM journals, talked about at SIGGRAPH. Now it's part of a thing that you can buy. Actually, no, you can't buy it. You have to subscribe monthly. But this is a lot of really interesting research that solves some of these issues and starts to give you more meaningful data. We can crunch the numbers and calculate motion vectors and detect larger moving objects even in the noise of trees, even from moving camera platforms. Now there is another way of detecting camouflage that involves using less data. In World War II, there were a number of guys who were colorblind. They could see less color information than regular folks, and that actually enabled them to pick out camouflage units with a greater degree of accuracy and speed. And going back to movies and our analogy of compositing, I had a friend at an animation studio that I worked at who was colorblind, which was the end of his dreams of being a professional colorist. But it did mean that he was fantastic at picking out bad composites. He could look at a composite and immediately see through the proper color match data that the values are not quite correct. That lightness and that darkness were not actually accurate and not going to show up really well. So sometimes the absence of confusing and conflicting data will bring actual differences to the fore. So, like this shirt being a different color than that background might not jump out at you until you actually remove some of the other details and see that silhouette a little bit more clearly. And it's also the way that machine vision often works. We know that facial recognition is pretty advanced. Specific shapes like apertures of rifle scopes and spotting scopes are really easily identified by machines. But usually the way that they do this is by throwing away the color data and looking for values. So oftentimes limited data is the way to actually see stuff faster. Now, let's go to our compositing tools and experiment a little bit with some of the different ways that we can make camouflage devices more visible by changing values, by changing color, by highlighting edges, by emphasizing some of the stuff that makes camouflage fail, that makes camouflaged objects stick out. We can just highlight information that is here. We can look for sharp edges and try to pick out some silhouettes that way. That might be something. We can experiment with some false colors. Because camouflage is going to be living inside of these green and brown areas, we could throw out red and blue color data completely and then just spread greens and browns across the whole area. Now we can see the difference between brown and green a little bit clearer. And now that we have these differences between what are normally close tones kind of expanded and exaggerated, we can draw lines around those and pick out some things that look like they shouldn't be here. Well, we are definitely getting some tree trunks up here, some tree branches down here, but we are picking out some of the camouflage that is here that isn't supposed to be here. And it doesn't have to be this extreme. Sometimes just a gentle change of the color palette, might help us pick things out that shouldn't be there. The issue is that I already know where the camouflaged kid is, and so it's really easy for me to build a color palette that will highlight what I already know is there. The problem is building something that will work across different camouflage and different vegetations at different times of day and different times of the year and in different parts of the world. That is where the machine learning probably comes in. But some of these tools will be really helpful in helping either humans who are on watch or machines who are triggering alerts to have a better idea of what's going on in the environment. And you can rest assured that other people are already working on this. Some cameras have this technology built into them already. For the purpose of exposing an image properly, false color palettes are often used that completely change out the color data for exposure data and allow you to see exactly where certain values lie. So this is what one of those false color modes looks like inside the Sony camera. It's not great for camouflage, but it's interesting to play with, and I'll just say for the record, this is only the third jankiest camera rig I have ever built. So sometimes the answer is more data, more raw information. And other times it's looking at less of the information. But the real sweet spot, I think, where the magic potentially happens is when you selectively pull from a bunch of different data sources to look at only what matters most. When you use the differences in data sources to figure stuff out. Satellite imagery is probably the best example of this because a lot of the imagery satellites that are up there have multiple cameras, like this rig, that capture multiple data across multiple bands. So like your red, your green, your blue, sort of. They capture spectral information across a huge swath of information, and then they subtract certain bands from other bands to try to figure out what is dirt, what is dry dirt, what is wet dirt, what is vegetation on the ground floor, and what is the canopy of trees. And I've been digging around inside of some satellite imagery data for the purpose of geospatial engineering, and it's really fascinating the way that some of the different land cover usages are calculated using this data. But it doesn't happen quite as much in a handheld configuration, and there's a bunch of reasons for that. One of them is processing, but the other is simple physics. If your satellite is thousands and thousands and thousands of miles up, it doesn't matter that these lenses are a little bit far apart from each other. But when you're shooting stuff by hand, up close, the parallax caused by these different distances is not great. I can't actually get stuff to line up perfectly pixel to pixel once I get too close to the cameras. I need a way to fit all of these things tighter together so that I can actually determine whether a pixel is this much red, this much green, this much blue, this much IR, this much heat, etc. But now that brings us back to another film-making analogy. Would you guys like to know what is the best, most advanced compositing ever done in a motion picture? It is not The Matrix, it is not Lord of the Rings, it is not one of the Planet of the Apes movies. It is, of course, Mary Poppins.
Mary Poppins, you look beautiful.
Do you really think so?
Cross my heart you do, like the day I met you.
So, in 1964, Ube Iwerks and some Disney engineers, but they did something truly magical. They built a system that used multiple cameras, just like I have here, but they used a special beam splitter so that both cameras were filming through a single lens. And one of those cameras recorded a full color image, just like this one. And the other camera used a beam splitter that peeled off just a tiny sliver of the visual spectrum. I think it was 590 nanometers, a sodium vapor light. And that let them get a perfect matte. And this was the gold standard of optical printing technology. This was the best compositing technology that existed easily up into the 90s, which, ironically enough, is when that camera vanished. It was so cool and so advanced that they couldn't really replicate it. They couldn't figure out how to make any more of these prisms that worked the way the first one did. And in the 90s, it got lost on the set of Dick Tracy, of course. Fortunately, there are people on YouTube who want to experiment with bizarre, esoteric, historical, and advanced futuristic technologies even more than I do. So the Corridor crew guys, working for Corridor Digital, worked with Paul Debevec to build a modern working replica of this beam splitter, and guys, it's even better than I could have imagined.
Paul recreated the physics of the sodium vapor process, but he did it with all off-the-shelf components. Instead of a custom beam splitter, he used 2 filters. And instead of 2 strips of film, he just used 2 cameras.
If you ever think your rigs are janky, they're all janky.
Now, admittedly, it only solves the problem of the edges, but it blends the 2 images together in the composite so perfectly that it's almost indistinguishable.
Oh, wow. You're zooming in on it. You are not afraid of your matte lines.
The compositor still has to get the colors right. He still has to get the white and black values and gray values and lightness and darkness correct. And that motion still has to work. But those edges that usually catch your eye make you realize that something is not right. Something is where it shouldn't be, goes away completely. And it was solved through really simple and straightforward techniques. Now, my question to you is, am I going too far down the rabbit hole of this 1964 lost Mary Poppins camera? Do I talk about movies too much? It could be that I'm just biased because I used to work in the film industry. In fact, back in 2009, I was at SIGGRAPH, and you can look up the paper that I published, and I talked to Paul Debevec. So this is kind of my world, my pre-T-Rex world. But on the other hand, I don't think that it's too much of a stretch. I think that information gathering tools and filmmaking tools have so much overlap. Data processing tools, machine vision tools, They have so much in common that I actually think the overlap is not just, justified, but thinking about some of these things through the lens of the other discipline is something that will generate new thoughts, new ideas, and possibly even new results.
I'm Mary Poppins, y'all!
So, what's the point of this video? Did we invent something new? I mean, obviously not. Ubiworks invented this back in 1964, and it works better than this. The point is not to figure out something that's never been done before. If this could be done in Hollywood in the 60s, a lot of this really complicated stuff is being done in satellites in the 70s and the 80s, and a lot of this stuff is coming to the modern military-industrial complex basically now. My point is not to invent something new that's never been done before, but to make you guys more aware of kind of how this stuff works, and to understand that this is extremely simple and it's actually really accessible. These devices right here are $2,000, $1,000, $400, $200, so you can cobble this together and do your own experiments really simply. Everybody has probably figured out by now that the infrared world is no longer the exclusive domain of the United States military. Almost everybody can see into the dark at this point. You have to assume that infrared light discipline is just as important as visible light discipline now, and thermal is the same way. You should have a thermal device because you will die without one, obviously. But you should also have one because they're fun to play with. You should get one to start experimenting and learning how the world looks in this other spectrum, because this is kind of the future. And it's so accessible that it's just fun to watch people make liquid nitrogen ice cream with it, for example, or come out into the woods and see which of your pieces of kit work in the environment, and have a better understanding of how people are going to be defeating certain types of camouflage, whether it's, you or other people. So thanks for watching that video. If you are new to the channel, you may not know that T-Rex Arms makes and sells tactical equipment. And even the stuff that is not camouflage, like this, we still pay attention to across multiple different spectrums. And if you did know that we made a bunch of camouflage and been watching for a while, you know that we have changed color schemes occasionally. Sometimes it's regular supply chain stuff from the mysterious events of 2020, but sometimes it's because we wanted to make sure that we had stuff that was neutral in the IR color space, something that didn't stick out or cause too much color contrast, and that's been one of our goals moving forwards with all of these products, camouflaged or not.